In this lecture, we'll be studying time series differencing and integration. The first thing we need to introduce is this backwards operator. So if we're given a time series, yt, the backwards operator b is defined in the following way. So b is operating on yt by backing it up 1 unit in time. If we back it up k times, right, b to the k, that takes us back k times in time. And it does nothing to it, so constant is fixed under the backup operator. So the idea here, if you had, say, b squared yt, you can think of that as b operating on byt. This is b operating on yt minus 1, according to the definition here. But then b operating on yt minus 1 backs you up to time yt minus 2. Recall our definition of the ARMA-PQ process. So the ARMA-PQ process is a time series defined in the following way. So we have a white noise process, our epsilons, and we have parameters mu, phi1 up to phi p, theta 1 up to theta q, and we have the defining equation being this equation 3 here. Yt differs from its mean today, with a memory piece of how it differed from its mean yesterday, down to a memory piece of how it differed from its mean p days ago, plus a new noise term, and then we have a piece of memory for yesterday's noise term, down to a piece of memory for the noise term from q days ago. We can rewrite this using our backwards operator. So first, let's take this equation 3 and just rearrange it. So let's bring all of these terms for the autoregressive piece over to the left-hand side of the equation. That gives us this here. And then we keep the epsilon t and the previous noise term on the right-hand side of the equation. With this, we can introduce our backwards operator. So the way we're set up here is this is the left-hand side of the equation, and this is the right-hand side of the equation for the ARMA-PQ process after we've rearranged it. And we can rewrite things. So here we have yt minus mu minus phi1, but note that this yt minus 1 can be written using the backwards operator. So we can rewrite that as byt. Right? The definition of that backwards operator tells us that byt is yt minus 1. So we're using that here. And also recall that the backwards operator does not affect a constant. So b times the constant mu is also mu. So we can take this mu and write it as b operating on mu. And we can do the same for each one of these memory terms. Recall that here, so we have phi p, but now yt minus p can be written by backing up yt p times. And because mu is unaffected by b, we can also apply the difference operator, b times to mu. And what we can notice here is we can factor out our b terms. And so what will remain here will be yt minus mu minus phi1 And let's bring that b out. And what's left in here is yt minus mu. For this term, we can factor out a b to the p term. And what remains? Yt minus mu. And we now see that yt minus mu is common to each of these terms. And so we can write this as yt minus mu times the quantity. For this term, we'll have a 1. For this next term, we have a negative phi1b. For the next term, we would have a negative phi2b squared. And all the way down to the last term, we have a negative phi p b to the p. So that gives us a nice way to rewrite that left-hand side of the equation that defined the ARMA PQ process on the previous slide, this here. So we've rewritten this left-hand side. And notice what we have here is yt minus mu and a polynomial in the backwards operator. We can take a similar approach to this left-hand side. Note that the backwards operator can also operate on our white noise process. So the backwards operator operating on epsilon t brings it back to epsilon t minus 1, and we can apply that on the right-hand side here. So this epsilon t minus 1 we're writing as b epsilon t, and we do that for each one of these terms down to b to the q epsilon t. And we now see we have an epsilon t common to each term, which we then factor out. And inside we are left with, here we have a 1 for that epsilon t. And we have a negative theta 1 b. And we have a similar term for the second term, so we have a negative theta 2. But this time we will have b squared. And we go all the way down to finally a negative theta q b to the q. And we see now on the right-hand side, we also have a polynomial in the backwards operator. Bringing this all together, we see that we can rewrite our ARMA process using this new version, where on the left, we have a polynomial in the backwards operator, and that captures all of the AR behavior. And on the right, we have a polynomial in the backwards operator that is picking up all of the moving average, order Q behavior. And these polynomials can be used to determine the properties for stationarity for yt, which would be done in a separate lecture. Now, since we have our backwards operator, we can then use that to define some other operations on time series, the first of which being differencing. And so we define our differencing operator, delta, in terms of that backwards operator in the following way. So delta is defined as 1 minus b, and we see how this works. So if we difference a time series, delta yt, that becomes, so delta yt becomes this 1 minus b operating on yt. And if we distribute this operation, we have yt minus byt. Byt, by the definition of backwards operator, is yt minus 1. So we see delta yt is yt minus 1. And the idea is this gives you a new time series. So if you were given y0, y1, y2, y3, the way that delta yt is defined is you're taking adjacent entries in your time series and taking their difference. So the first entry in the time series of delta yt would be y1 minus y0. The second entry would be y2 minus y1. The third entry, y3 minus y2, so on and so forth. And it's important to note that when you take a time series, so if you have data, say you have your time series data, y0, y1, up to yn, this data, there are n plus 1 points, right? We're starting the numbering at 0 and going to n. But if you note, when you take your delta yt, and you have that pairing, y1 minus y0, and then y2 minus y1, up to yn minus y and minus 1. If you use the numbering, just look at the numbering of the first term, the first y in each of these terms, y1, y2, up to yn, you have n terms. So in the yt times series, you had n plus 1. In delta yt, you have n. So when you take this difference, you do when you have these finite time series like you're getting from data, you reduce the number of entries by 1. And this will be akin to the idea of taking the derivative of a time series. And you can think of that, one way you can think of that is if you look at this defining equation, imagine if you add, so you have delta yt is yt minus yt minus 1. Of course, we can divide both of these by 1. But the reason we're dividing by 1 is notice that that's the time step. So this is how yt is changing. And time is changing from time t minus 1 to t. So you can think of this as delta yt over delta t. It's yt minus yt minus 1 over delta t. And so you can think of this as differentiating a time series based on the idea of writing this delta yt as a difference quotient where the delta t is in fact equal to 1. As an example, if we have asset prices and returns, so first let capital PT be our asset price at time t. Little pt is the log price, and then RT will be the log return. And so remember what we have here, that think of P, suppose that PT minus 1 is 100 and PT is 110. So you would say the value of your asset has increased by 10% between time t minus 1 and time t. In that case, 110 over 100 is 1.1. So what we have here is what we call the gross return on the asset. And when we take the natural log, that gives us the log return. And the log return is a very commonly used return in financial modeling. And so let's actually look at what we have here, at the relationship between these things. So your log return, by definition, is the log of the ratio of these two asset prices. But we then use the property of natural log, that the log of the quotient is the difference of the logs. And we then notice that these are the log prices, which are the little p's. So this is little pt, and this is little pt minus 1. And we then see that that is nothing more than taking the difference of those log prices. So a time series for log returns is a difference, or here we're saying a first difference, of the time series for log prices. Now this suggests something. When we say the first difference, we can do it more than once. So if you have your time series, y, t, this is our difference as we just defined it. But we can iterate. So we can use the difference operator again. So delta squared, yt, would be, we can rewrite that. And what we have in the parentheses here, we already have an expression for. We have what this delta yt is yt minus 1. But we can now distribute this difference operator, which gives us delta yt minus delta yt minus 1. This first term, again, by definition, is yt minus 1. And our second term, we simply apply our difference operator to yt minus 1, which, recall, the difference operator is 1 minus the backwards operator, or yt minus 1 minus b yt minus 1, which is yt minus 1 minus, and the backward operator backs up yt minus 1 to yt minus 2. And we see that we now combine these two terms. So we have a yt. But notice here, and we should be a bit careful, maybe we should rewrite this. So this becomes, we still have our first term here, yt minus 1, and then we're subtracting this new term, yt minus 1 minus yt minus 2. And we can now simplify this. So we see we have a yt, but notice here we have a negative yt minus 1 and a negative yt minus 1. And so we have minus 2 yt minus 1. And here we have a minus yt minus 2. And this would be the second difference of our time series. And notice that because you have time t minus 1, time t minus 2, if you have, as we had before, a time series where you start at time 0 and go to time n, so n plus 1 terms, the first difference will give you a time series of length n, and the second difference will give you a time series of length n minus 1. So each time you do one of these difference operations to your time series, if you're dealing with data, think, finite time series, you're going to lose one term. And as before, we can think of this as the second derivative of a time series. So again, if you were to, say, divide this by delta t squared, delta t is 1. So we can write it like that, but you can think of this as your difference quotient for the second derivative. Now, of course, if we're taking derivatives, we, as students of calculus, want to go the other way and integrate. And we can do that. And the inverse of addition is subtraction, right? So when we're differencing, we're doing a subtraction. Here to integrate, we do an addition. So suppose we're given a time series yt. The integral of yt is the time series wt, defined in the following way, where t naught is some starting point in time, and this wt naught is the initial value of the process. And remember, when you learn integration, when you take an integral, an antiderivative of a function, you introduce an arbitrary constant and get an entire class of functions. If you want one function, you need an initial condition or an initial value to tie you down. The same holds here. So we have an initial value here. You can think of it from what we were saying before. If you difference a time series, you decrease the number of data points in a finite time series. If you integrate, you increase the number of data points, and that requires the addition of an initial condition. Again, similar to how things work when you're doing antiderivatives. And we stated here, integration of a process is the inverse of differencing. So this integral, Wt, if we difference it, we get our original Yt. And notice this is this integral is coming from the idea of accumulation. So you're accumulating the previous values, the values at times prior to Yt, up to Yt. So let's look at our example again. So recall we have our variables, capital PT is the asset price, little pt is the log price, RT is log return. And we established that these log returns are the difference of the log prices. Well, if we want to go the other way, so let's integrate that RT. Let's integrate the log returns. And so a way we can write this is the integral from time 0 to time t of Rs. Note that we have this is our initial value, what we had called W sub t naught in the previous slide. In this slide, we're saying that t naught, we're starting at time 0. So this is our initial condition, which is our initial log price. And then using that previous definition, we simply accumulate, we start with that initial condition, and then we accumulate, starting at that time for the time series, in our case R, and we accumulate them by adding them up until time t. So R1 plus R2 up to RT. Now we note that RT is delta PT. So we simply make a substitution. So R1 is replaced by delta P1, R2 by delta P2, so on and so forth up to RT times delta. RT is replaced by delta PT. And we know from our definition now, delta PT is this difference of the time series for the p's, little p's. So we have our P naught, delta P1 is P1 minus P0, delta P2 is P2 minus P1, up to delta PT is PT minus P1. And what we now notice is the pairing. Our initial condition, P0, those pair and cancel. The P1s cancel. This P2 has a partner in the next term, so that cancels. If we go to the other end, we see our PT minus 1s cancel. This PT minus 2 has a partner in the previous term. And so we see everything cancels except PT. And this is a confirmation that the integral of this log return process is in fact the log price. So we see how you can go either way. If you difference log prices, you get log returns. If you integrate log returns, you get log prices. So the idea here is that now, given a time series with this backward operator, which gave us the difference operator, allows us to take these differences of time series, which is akin to differentiating a time series, and we can also integrate a time series, and we see that our definition of integration and differencing give us these inverse operations for time series. And this will be incredibly useful for things that we will be doing going forward.